Hello, Honors Chemistry, and welcome to the Chapter 8 and 13 Review, Part 2, where we're going to we're going to work through some problems together. So, first of all, let's see. Obviously, in order to do Chapters 8 and 13, there is the assumption that you recall Chapters 5 and 6 and 7, and probably like 2, 3, 4, the whole cumulative thing, right? So let's go ahead and pick a few of these to work through together, right? So here, we have one that says excess hydrochloric acid, right, reacts with 5 grams of magnesium. How much heat is released by the reaction, right? So first of all, keywords, react, right? React means that at some point, right, we're going to have to do a mole ratio, right? That's what that tells me, right? We're going to have to do that mole A to mole B at some point because we have a chemical reaction. It also tells us that we're going to have to write out a reaction at some point, right? And that's going to be necessary for part of our problem. We are told that there is excess hydrochloric acid, right? And we only have one piece of information as our given, right? Which is a mass. Here we might see this and we might be tempted to think of that as a given, but what is that? Right, that's not a given, that's one of our conversion factors. That's our heat of reaction, which says that there are negative 460 kilojoules of heat equal to every moles of whatever, right, moles of reaction, which we will edit once we figure out some of our bits and pieces, right? And our question is obviously how much heat, and we know that heat is in units of joules or kilojoules, right? Doesn't really matter. So now we can go ahead and do the problem. First, we need a chemical reaction, so let's do that. We have hydrochloric acid and magnesium, so we have HCl, aqueous, it doesn't say, but I'm telling you that, right? Plus magnesium, which we know would be a solid because it's a metal, produces magnesium chloride because that magnesium will switch with hydrogen. So magnesium chloride, it would be aqueous because there's water present, and H2, which would be a gas. We would balance, right? So then now we can edit this down here to talk about one of our pieces, right? So this is going to be equal to 1 mole of magnesium. We could also say that negative 460 kilojoules are equal to, I guess it doesn't really matter, but 2 moles of HCl, for example, right? Or we could say 1 mole of magnesium chloride or 1 mole of hydrogen. All right, so now going back to the problem, I need to get to heat from my mass of magnesium, right? So if we think back to what we were doing earlier, which was working with that roadmap from the previous one, right? We are given mass, right? We are given a mass to begin with, mass of magnesium. So we're going to call that A, right? And we are trying to get to a heat of reaction, right? Which means we're going to have to go from grams of A to moles of A, and then what else did I say? How much heat is released by the reaction? So actually, in this particular instance, we don't need to do a limiting, right? So we're going to go from there to moles of A, and then where are we going to go? Right, we're just going to go straight up here to heat, right? Because we don't have to do any limiting reactants, we don't have to do anything else. We're going to do from grams, use molar mass to get to moles of A, then we'll use heat of reaction to get to our heat. Because we already know that magnesium is our limiting reactant, right? And we don't have to figure that out, so we don't have to do anything extra, actually, right? So in this case, no, we don't have to do a mole ratio. Nope, not this time. All right, so we'll take our 5 grams of magnesium and molar mass, because that was our first step, so molar mass of magnesium to get to moles of magnesium. And then we'll do that, right? So that says for every 1 mole of magnesium, and again, that 1 mole comes from our balanced equation, is 460 kilojoules of heat, right? That cancels, and then we would just do that math, bearing in mind, right, that negative sign, which means that energy is released, and this process is exothermic, yes? All right, let's do another one. So on this page, let's do this one. So it says 1.33 grams of sodium iodide are added to water, right? So here's one of those times we should think to ourselves, we have something going into water, right? And then it says molarity of the solution. So do we need to write a reaction here? Right, no reaction here because that's not what's happening. All we're doing is making a solution. That's it, right? So here is my solute, right? and are added to this, and it says the volume is unchanged. So this is my volume of my solution, right? And so then I just need to get everybody into the right units. So I'll take my 1.33 grams of sodium iodide, and then I will get the molar mass of sodium iodide, 149.89 grams of sodium iodide for every 1 mole of sodium iodide. And then I will divide by my volume, right, of my solution, and grams of sodium iodide cancel. I'm left with moles of solute over liters of solution. Yes? All right. And like we said in the previous videos, right, we could also just take this answer, right, so get that number of moles and take our number of moles and divide it by my volume, right, and that would also get us our molarity. Yes? Okay, where this would be our number of moles. All right, next up. It says that we have 20.5 millimeters cubed of solid aluminum, right? What kind of information is that? Right, that is a volume of aluminum. It says are added to 20.5 milliliters of aqueous copper 2 chloride in a test tube, right? So here we have a volume of a molarity, and I would like to know what color is the solution at the end of the, what's that keyword? Reaction, right? So, first of all, I know that there's a reaction, right? And here is my volume, here is my molarity, right? So this is 0.25 moles of CuCl2 aqueous are equal to 1 mole of CuCl2, right? Make sure we write that out so I see it and I know that, right? And I also have a volume of aluminum solid here, right? So, what is this question really asking? Right. It's asking us for the color at the end, right? Meaning what does our vessel look like at the very end of the process, which really means I need to think about, right, what's the limiting and what's the excess, which again, like we've talked about before, every time we know the amounts of both reactants, that's really what the question's asking anyway, right? So we already knew that that's what we were going to have to do. So let's go ahead and do that, right? So if we take a look, we're going to first start by writing a balanced chemical equation, which says aluminum solid plus CuCl2 aqueous is going to give us our aluminum chloride aqueous plus new copper, right? And then we'll go ahead and balance. And then we've got to figure out the limiting reactant, right? Okay, so I made a quick mistake, and so we're just gonna put all the work up there and you can sort through it. But basically the goal is to calculate the limiting reactant. So we start with our 20.5 millimeters cubed of aluminum, use the SI conversions, and then we cube them because we're talking about volume. Then we use the density to get to mass, we use molar mass to get to moles, and then I picked copper. You could pick aluminum chloride, it doesn't matter. And we can stop at moles because we simply need to know which is limiting and which is excess, right? And then I would start again with the amount of copper chloride that I have, use its molarity, and then do the mole ratio again. And then when I look at my two potential amounts of copper, I would see that indeed the aluminum is our limiting reactant because it produces the smaller amount of copper, which means that there will be excess copper 2 chloride aqueous, which means that the final color of the aqueous portion will be blue and clear, right? Whereas if copper chloride had been limiting, the aqueous portion would be colorless and clear. Yes, does that make sense? All right, so basically if we want to talk about anything at the end, that requires knowing which is limiting and which is excess, right? And remembering some of the basics from our labs and demos. All right, next up, what volume of 12 molar hydrochloric acid is needed to make 5 liters of 1 molar hydrochloric acid? And what volume of water is needed? And we can assume that volumes are additive. So here we have hydrochloric acid and we have hydrochloric acid. So not a chemical reaction, right? There's no reaction happening, right? All we're doing is, if we take a look here, right, diluting it, making something less concentrated. So here we just need to make sure things match, right? So here if this is my V1 and my M1, right? And then this could be my M2, right, for example. And let's go ahead and label it, right? This is my stock, and this is my dilution. So that way it's crystal clear, right? So M1 will be 1 molar times my V1, which is 5 liters, is equal to M2, which is 12 molar, times my V2, right? And we're going to solve for our V2. So we'll take our 5 divided by 12. And now unit here is going to be what, right? Those cancel, so my unit is going to be liters, right? And that is my volume 2, which is going to correspond to my stock, right? So this is the volume of stock needed. And again, how much are we making total? Right, I'm trying to make 5 liters, so 5 liters total minus my 4 point this many liters of stock is going to give me the volume of water. Yes, approximate volume of water, right? Because again, if we were to make it for real, right, there's no guarantee it would come out to that exact number. Yes, does that make sense? All right. Let's see if there's another one. Here. What volume of 2 molar hydrochloric acid is needed to neutralize that, right? Neutralize is a keyword for, right, react. That's what that means. So then, here I would like to know the volume. So how many liters of this? And so again, we would say, this means 2 moles of HCl are equal to 1 liter of HCl, conversion factor, right? And here we have a mass of my compound, right? And this is going to be my given. So we'll start by writing a reaction that says we have some aqueous HCl, which we will react with some sodium carbonate, which would be a solid, right? And that will produce some NaCl, aqueous, because it dissolves in water, some H2O, right? And some CO2. And then we will balance, and we'll be good to go, right? Now, let's go ahead and think about our problem. So this is going to be our given from where we start, and this will be a conversion factor at some point when we're ready to convert between moles and volume of HCl. So we have our 25.8 grams of sodium carbonate, and then we will use our molar mass to get to moles. So we have our molar mass to get to moles. And then we're going to go from moles of sodium carbonate. So for every 1 mole of sodium carbonate, I require 2 moles of HCl. And then I know there's my molarity, right? For every 2 moles of HCl, that is equal to 1 liter of my actual solution. And that's my answer, right? Those all cancel. I have solved for what volume of hydrochloric acid is needed to neutralize that mass of sodium carbonate. Yes? All right. All right. Thank you for listening. Be good, and I will see you soon. Bye.